So, hi everyone, I'm Alex, and I did my project on quantum mechanics and Bell's inequality. And I chose this project because I'm really interested in the more theoretical aspects of physics, sort of like the cutting edge kind of stuff. I find it fascinating. But you might be looking at this right now and you might be wondering, why do you care about quantum mechanics? Let me tell you right now, you should care about quantum mechanics because in a couple of years you might be seeing a lot more of it than you actually know. So up here, these are just 3 examples of things. Unbreakable computer codes, super fast computers, and very advanced microscopes. Those are just 3 possible future technologies that quantum mechanics could bring to us in the next couple of years. But aside from quantum mechanics, I focused on Bell's inequality, which sort of, as I said in the title, it proves what's called spooky action at a distance, or sort of the way that quantum mechanics works. And so Bell's inequality comes out of the Bohr-Einstein debates. So when quantum mechanics was first starting out as an established science, there were sort of 2 different ways of thinking about it. There was the Copenhagen model, which was sort of the accepted model by Bohr and his followers, that essentially said that a subatomic particle doesn't have a set position. Its position is only determined by a wave function, which says you have all these different positions that it could be at, and you don't know exactly where it is until you test for it and you measure exactly where it is. Now, Einstein was really in favor of sort of a deterministic idea. He wanted things to always have a set position, or like a set velocity. He wanted things to be set. And so he was saying that quantum mechanics was incomplete and that the probability functions weren't correct. And so he and Bohr sort of argued over a couple of different science conferences, and in the end it seemed like Bohr had won the debate until Einstein came out with hidden variable theory. So hidden variable theory was the idea that quantum mechanics is incomplete and that there are some kind of hidden variables within quantum mechanics that once we identify them, we would be able to find set positions for these subatomic particles without having to test for them. And so Bell, after hidden variable theory was published, it sort of created a lot of waves in the science area. But it wasn't until a few years later when John Stuart Bell took a look at hidden variable theory that he came up with something that sort of dealt with the debates. What he did was he created an experiment that would test whether hidden variable theory was correct or not. And that's where Bell's inequality comes in. S is essentially the result of that experiment. And so in that experiment, you would take a set of entangled photons, and you would sort of shoot them out in like a V. And at the end of each V would be a polarizer. And each of these polarizers would be set at a different polarization angle. So these photons would go through, and they would be polarized differently. And then on the other side of the polarizer, you would have a single photon counting module. And what these counting modules would do is whenever 2 photons hit them at the same time, it would register a coincidence. Now, as you change the sort of polarizations, you change sort of the way the photon moves, and you change how many coincidences there are going to be. So, what John Stuart Bell theorized was, if you are to use hidden variable theory, and you are to use the quantum mechanics predictions with hidden variable theory, then your polarization correlation, or the number of coincidences you get for these different combinations of polarization, when you add those up and put them into the equation for S doesn't actually have any kind of actual definition, it's just a given number. But if you put those different polarization correlations into the S value equation, if HVT is true, then that S value is going to be less than 2. So what's really important about this, it set up an experiment that would test whether or not this was true. And when this experiment was done, the experimenter was able to attain an S value that was greater than 2, thereby disproving hidden variable theory and proving that quantum mechanics works with probabilities. And that was huge because quantum mechanics, because of the way the probabilities worked, it would actually violate that idea that Einstein had where the speed of light is the universal speed limit. Because essentially if you've separated those entangled photons very far away, as soon as you measure one, because they are entangled, you know the qualities of the other one. And so that was essentially a faster-than-light transmission of information that broke some of Einstein's laws. And so that was a really big deal. So when it was found that you could break this inequality, it was called by some the most profound discovery in modern physics. But what you probably want to hear more about is how this is going to create cool applications. So what I looked at more was the idea of uncrackable computing codes. And so this is actually not too different from the way we do computer codes right now. One computer would send a code to another, and the other computer has the code with which it can decode the information sent. But the way that this becomes uncrackable is if computer one now sends a stream of polarized photons across, the other computer knows how they are polarized and can sort of unpolarize or decode them. But because of the way that quantum mechanics works, if anyone tries to interfere and intercept this information, just by observing that stream of encoded photons, they're actually changing the way the photons are. And that way, it becomes useless to them. And so that's how it becomes like an unbreakable computer code. And this has actually been tested over short distances by some banks, and they found that it does work. And so that's what I had. I can take some questions now. Amelia?
Is this like something they would use to send different like secret messages back and forth maybe? Like codes? Or is it more just like what is the use of the codes?
It could be used for that. It could also be used for even just like authenticating, sort of like when you have to go into a bank, you have to put in like a password. This would make it so that like no one could steal your password when it's being transmitted.
Oh, okay.
Just because by looking at it, they would be changing it.
How close do you think we are from actually using these types of unbreakable codes?
Well, like I said, some of these have been tested. Right now they only work over short distances, so they're sort of still in the testing phase. But if they keep testing, I think it could be very recent. Also, earlier I mentioned like super powerful computers. Like Google is already doing a lot of work with quantum computing. So some of these technologies, you could see them in the very near future.